I'm Dr. Kant Kanyasoke, a Ugandan in East Africa, but working in South Africa at the Cape Peninsula University of Technology. I want to talk to you today about solar water purifiers, okay, for rural domestic homes in Africa. Why? Because if we look carefully here, typically, especially in the dry season, our people in Africa collect water from certain pond. This lady here is going to use that water to cook food, to drink, to wash clothes, and so on and so forth. How many of us would like to drink such water? Hardly any. So, my research deals with providing units such as that one to this lady here, so that when she collects this water from wherever she collects it, she can put it in there, spread that, put that thing in the sun, that machine in the sun the whole day, and throughout the day collect some water there, some pure, clean water there for drinking purposes. For drinking purposes. The water, there will be water which will remain in there. It will be hot enough to have killed most of the pathogenic microbes, so that even the water which remains in the solar water purifier can be used. So that's my research. Now, several designs have been developed. We have developed several designs with my students at Cape Peninsula University of Technology. In this presentation, I'll talk about only 5. I'll talk only about only 5. So, I'll give you the technical key performance indicators, and at the end of the day, we'll share a light moment in this research. And how? I give you a brief science of solar water purifiers. I give you the designs investigated, the 5 of them. I give you my KPIs. I give you the testing of the designs, and we shall look at the results and conclude eventually with the light moment. The science of solar water purification. Ladies and gentlemen, solar water purification is a fairly easy process. You have a basin there. Inside that basin, you have some amount of water to a certain depth. You have a glazing there, and you put this thing in the sun. Then solar radiation comes from the sun, enters here. Some energy is lost at the surface. But a fraction, G in, enters the glazing. Now, what happens to that G in? When G in goes in, when that fraction goes in, some of it is absorbed by the water, some of it will reach the black surface at the bottom, in which case this thing heats up. The water heats up. As the water heats up, some of it starts to evaporate. And as it evaporates, it reaches the glazing there. The glazing is cooler than the hot water here, so it condenses on the glazing. As it condenses on the glazing, the droplets, because of surface tension, stick there, and because the glazing is inclined, they start dripping, drip, 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 and come to this channel here. In that channel, it's inclined slightly. Then, once they drip there, then we can get the water, the pure water out here. The interesting thing is, it's very hot inside there. The germs, which this lady picked from wherever she got the water, are killed. The salts, they absorb, and the suspended material remain inside there. So she gets very, very clean water here. So that's the basic science. That's the basic science. Now, what are the designs that were investigated? 5 of them. Here we have one of the first one, which allows condensation inside and outside. We can have condensation here, we can have condensation outside there. And the glazing here is double. There are 2 sheets of glazing. We have also 2 sheets of glazing there, but here we allow only condensation outside here. Inside there we have a fan which extracts steam. We don't allow condensation. For some reason, we don't allow condensation on the glazing. We let it go out. Then that is me with my most revolutionary design, a portable one, which is foldable. You just lift this thing, go to wherever you want to go, in camping, in the bush, wherever, erect it within 15 minutes, put in your water, and then you get your pure water. So that is the third design. The fourth design is a non-drip one. Okay, this one here is single glazing, and the angle there is made steep so that you have minimal drip bar, because sometimes, as we shall see, some of the condensate tends to drip bar. The fifth one is a more gentle angle which allows more radiation to reach that, but this one we made it track the sun. We put it on a mounting on a sun tracking pillar, so that it can always face the sun east to west. So those are the 5 designs that were investigated. Let's see. So these devils are as different as they come. How then do we compare them? So I define 10 key performance indicators grouped in 4 groups. Number 1. I define functionality. So to compare them, let's first define functionality. That is, say, this purifier, it's here. Yes, I have bought it. Does it do its job? And there are 2 key performance indicators there. 1, the number of liters of water collected per day. And 2, the amount of solar energy, free solar energy, that is utilized. So those are 2 key performance indicators. Then I have a key performance indicator on quality. The quality of the purifier. I have bought my purifier. What is the quality of that purifier? And I measure that depending on the temperature of the water that is achieved inside the purifier. The higher the temperature, the better the quality, because then I'm able to kill most of the microbes. At 60 degrees centigrade, most pathogenic microbes, including those which cause cholera, those which cause diarrhea, E. coli, die if exposed for 3 minutes. So if my temperature can go up, then I have a good purifier. Then another one is efficiencies. Okay, there are 3 efficiencies that I'm interested in. The optical efficiency, which is essentially the fraction of the energy, the solar energy which has come and has managed to enter the glazing. The G in divided by what is actually incident on the glazing. That is one. That's an optical efficiency. Then there is the distillation efficiency, which is the energy which is required to distill the water that you collect. Okay, divided by the energy that has entered, that has reached the glazing. Thirdly, you have the total energy efficiency, which is essentially the total energy which is used to distill and to heat up even the water which has remained behind. So that that one as a fraction of the total energy that has reached the glazing. From an economics point of view, there are productivities. The glazing is the most important. It's the most important part of the purifier. So per square meter of glazing, I'm interested in how much water do I get. If I put it in purifier X, purifier Y, purifier Z, how much water do I get? So that is productivity, glazing productivity. Purifier mass productivity, these purifiers are of different masses. So for 1 kilogram of purifier, how much water do I get? Purifier cost productivity. Per $100 that I spend, how much liters do I actually get per day? Those are the performance indicators. Now let's look at the experimental tests. These purifiers, the 5 of them, were set up simultaneously in our compound at CPUT in Cape Town, and this is a typical installation. We have a weather station there, okay, and this is one of them. And from that setup, we did the experiments over a period of 11 days in February, summer, and the primary data that we got, total irradiance on the horizontal, diffuse irradiance, wind speed, ambient temperature from the weather station. Then from each of the purifiers, we got the glazing temperature, the steam temperature, and the water temperature every 30 minutes. So from that data then, we are able to compute our performance indicators. Results. The results are clear. Functionality. We see very well that the sun tracking unit outperformed all the others. Okay? That's functionality. Quality. We see that, again, the sun tracking unit, together with my portable unit, outperformed the rest. Efficiencies. My portable unit outperformed the rest, because its glazing was very, very thin. It was made thin so that it can be light, so that somebody can easily carry it. Then, but when it came to efficiencies, other efficiencies, the steep one, the one which is no drip, outperformed the others. This SP4 outperformed the others. Then we go to the productivities. On the productivities, obviously the sun tracking one outperformed them because it's always facing the sun. But it lost out on cost because of the cost of what? Because of the cost of purifying. Then the other parameters on productivity, you can see my special one outperformed the others on mass because it is very light. So for every kilogram of that one, you could get 250 mils per day. Then when it comes to useful power or heating power, okay, we find that it's our friend, the sun tracking, which outperformed the others. Let's conclude. It's clear that the sun tracking unit outperforms the others on functionality issues, okay, and on quality. It's also clear that high slopes are very good because they avoid condensate drip back, as we saw in solar water purifier number 4. Then we saw that the thin one, the portable one, the thin glazing one, is very, very cost effective. It provides very good quality. It is very easy to handle, and it gives reasonably high yields. However, we also saw that those with double glazing and external condensation perform very badly. In fact, we don't recommend it. We don't recommend it. Then, so, in summary, what do we recommend? We think the best design should be, assuming technical skills are available, should be a thin single glazing unit, like my portable one, but this time inclined at a steeper angle so that you can avoid a drip back, and allow it to track the sun so that you can use as much energy as possible from the sun throughout the day. Now, the lighter moment. You see, this is in Africa, but it's not for Africans alone. Our visitors and so on are welcome. We want them to have very good water. We don't want you people, when you visit us, to drink bad water. So it benefits you. But that aside, it can be used, the technology can be used elsewhere in the world where there is no running water, but there is good what? Sunshine. Now here, I show you a Chinese gentleman who came to my country, Uganda, in East Africa, as a construction worker, and then he fell in love with one of our girls. He got married to her.
1 minute.
Yes. He got married to her, and we gave her a name, or we gave him a new name, we gave him a new clan, and here he's explaining what actually, what actually happened. Let's see. Oh, what's this? What is your name? I'm called Nsuga. I don't eat the land, but I drink the water where the fish lives. So this gentleman who drinks the water where the fish lives, I'm trying to help him. That this unit here will help him avoid those funny diseases. Thank you very much, ladies and gentlemen.
Okay, any questions? Yeah, please.
One question, guys. I'm curious if you tried, instead of water, if you, for places where you can't find water, how about putting some green plants, green material, and put it in there and let it do the evaporation to collect the water as a way to...
Absolutely. That is a different project.
That's right.
That is a different project which my students are doing on solar crop drying. For him, he was discarding the water. For us, we are collecting it.
Yes.
Okay, that's a different project.
That's a good idea to do that,
Yeah.
Yeah. Please, yeah.
Usually the contaminated water has very bad smell, right? And it is very easy to evaporate and into the purified water.
Yes, I get you that the volatiles could easily escape and also go into the water. But what actually happens is that water is normally filtered. I think I showed you on the very first slide there is a filter there. So some of those things are filtered out. Now, but for the majority of water sources, that is not a very big issue. In any case, even if it were to be an issue, which is better? Should this lady drink that water she was picking as it is, or at least pass it through? That's the question. That's the basic question. But in general, those volatiles are quite limited. We take it. We understand.
Okay, please. Yeah.
Any biological inspection?
Oh yes. There are tests which have been done on this. Incidentally, this unit here is right. It was a gift to my mother on Easter. This is my mother's home, right in rural Uganda. I lifted this unit from Cape Town, South Africa, 6,000 kilometers to Uganda, after thorough testing in our food science lab. So the water is perfectly clean, perfectly clean. I would never, of course, give. When I go home, that's what I drink anyway. So I would never drink that rubbish water.
Okay, yeah.
There are a lot of water purifiers out there. Have you compared both performance and the cost?
Now, in terms of cost, first of all, yes, it's true there are other purifiers, but not in Africa for sale. So on the African continent, they're not there. So that is number one. Number two, in terms of cost, here we have used reasonably low-cost materials, okay? And there can be variations. Actually, there can be variations. The thing could be made out of local raw material. It could be made out of concrete. That is the size and so on and so forth. So it's affordable. Then thirdly, when it comes to comparison of costs, yes, from the US, a typical quotation gives something like $2,000. This unit here, we produced it at 3,000 rand. 3,000 rand is slightly below, just above $300. So you can see, $300 with several thousands of rand of dollars.
That's pretty cheap.
Yeah, very, very cheap. Very, very cheap. So really, this is the way to go. This is the way to go. And I have a small company, okay? I have some cards here, which is going into these solar things, okay? Solar water purifiers, solar crop dryers, solar heaters, solar PVs, and all that. And it's trying to tackle this problem for the African continent.
Okay, yeah,
Okay, I heard you have mentioned tracking system, solar tracking system.
Yes, yes, yes.
And I'm curious about is a single access or double access?
No, this is single axis. As you could see, okay, I don't have to go back. As you could see, it's mounted on a pillar, okay? And the sun comes like that, east, it's like that. So it's actually tracking every hour, intermittently. So after 1 hour, 15 degrees. After another 1 hour, 15 degrees. So at least that phase is kept. So it's single axis, the vertical axis. The vertical axis.
Thank you.
any more questions? Yeah, please.
And the design of this is apparently very simple, okay?
Yes.
But was the first moment that invention, how, when, and how do you design the first moment to this design?
No, well, okay, of course it looks simple, but what can I say? I think, yes, on the surface it looks simple, but it's a lot more difficult than that. That's why there are actually so many permutations. Here I've shown you only 5. But then if you looked at the pillar, there are so many others.
Yeah.
Okay? So the issue is, well, think. Water will evaporate, condense it, it will leave all the rubbish behind. So find a way of collecting that condensate. It's just as simple as that. It is easy, but the only problem is, though, it is slow. It is slow, okay? But so what? So what?
But the first inspiration for this is...
No, it's problems, my dear. It's problems. When I go home to Uganda, at home, I have a problem. I have to buy water. I have to buy bottled water to drink. Yet there is a lot of water around. So it's problems. How do I solve that problem? My mother, she's a cattle keeper. Okay, she used to drink milk. She never used to drink water. Okay, because the water is contaminated. So she gets visitors who want water. So what do? So it's problems. So you think a way, you try to find a way around those problems.
So
Just like other things, really. Crop drying. Our crops, 60% of our crop production in Africa rots or never dries properly. So somebody must solve that problem.
survival stimulates innovation.
Yeah.
Yep.
Okay. Now my question is, how much litter you produce in one day in that size?
Now,
still, yeah.
Yeah, they actually the productions were there, but say, let's look at this one here.
Yeah.
This one in Cape Town was designed for 5 liters a day. When I took to Uganda, because of cloud cover, I took it in April, okay? Because of cloud cover, it couldn't produce 5. It started producing 5 liters in June, July. But in April, it was producing 3.5. But that's good enough for my mother. That's good enough for my mother.
No, but usually, according to FAO, one family requires about 200 liters of clean.
Oh, you forget. First of all, those FAO things don't apply in Africa. Because I mean, they don't apply in Africa. I mean, they don't. Forget them. Because look at that, what that woman was collecting. Does FAO know about that woman? So forget those things. What we are trying to solve is a basic problem. Okay? And we are not going to be bogged by FAO, World Health Organization, I don't know what. No, we cannot. We cannot.
Okay.
Yeah.
Okay, thank you very much.
Thank you.